Okay, we're going to switch gears now. We're looking at data with means. Now we are switching to proportions where we don't actually have any numerical data per se, but we have categorical data. And from that we can actually get proportions. So it makes more sense to just go right into the example. So is there a significant difference in cancer prevalence in middle-aged women who have a sister with breast cancer compared to the general population? So proportions are percents. So we have 1%, 5, and then our set value, which is 2%. So the null here will be, there's no difference between these percentages, where the alternative is there is a difference. So we'll guess a small effect size here. That makes sense to me. Now these are H tests, so it's going to be 0.2 as small effect size. And then we asked about difference, so I'll say two-sided. Now we'll be using power p-test in R. So pretty similar to the t-test, only the H is the effect size now. So give us all the power, and then alternative, we're back to having to determine tails. And then if we need to calculate this H effect size ourselves, it's kind of a nasty equation, but pretty easy to punch in a calculator. It's the arc sine with the square root inside of one proportion, and then it's minus 2 times. So yeah, they're both 2 times the arc sine within the square root of a proportion. So kind of nasty, but it's doable. So looking at our example here, we just guessed, so we didn't have to worry about that calculation for now. We just plug in 0.2, do two-sided, and it tells us the proportion power calculation for binomial distribution. That's the arc sine transformation. We get 197 to get this test. So easy enough. Let's practice. Okay, so this first one here, we get one proportion, and then we get some trial data to get our test proportion. So now we need to actually use that equation. So we plug these in to this to get a very small number of 0.0007. So that's our effect size, and we'll say greater because we're actually, if males are greater than the average, so higher, which gives us a whopping over 12 million. Heads up, if you don't know about North Dakota, there are not even close to 12 million people, so I don't think we can actually test this. If we look at the second, we're again given the set proportion, but we actually have no information on the female rate. So we're going to just guess effect size here. Given the males was very low, let's guess maybe not quite as low, but still pretty low. And we'll say less because we're asking her if it's lower. And that still gives us 6 million samples. Still something not in the realm that we can calculate, but there it is. All right, two proportion test. Just like one proportion, but now instead of a set value, we have two proportions. We want to look if they're different. So we could ask, is a proportion of students who passed a stats course by one teacher different from that of students from another teacher? Maybe we're wondering, well, which class should I take if I really want to pass? And I guess maybe there's a small effect size, hopefully. And again, these are H tests. And then we're going to say two-sided because we don't care about difference. So very similar. One proportions. Again, we'll be using power now. It's 2p, so two proportions test, but what we put in there is very similar to one proportions. So what this looks like in R, we plug in our effect size. We're going to do two-sided, significant power, to give us 393 samples. Here's some more practice for you to try. Okay, let's dig into that. You see in number 1 here, we're given the raw data, and as I mentioned at the beginning of one proportion, this isn't numerical data, this is categorical. So yes and no, but from this we can get a proportion. We can see that yes equals pass, so for psychology, 1, 2, 3, 4, 5, 6, 7. So 7 out of 10 pass, so 70%, whereas in biology only 6 passed. So those are our two proportions. We can plug that in to get effect size, get negative 0.21, and we're asking about difference, so we just do two-sided, give a total of 356. For 2, we're asking about another thing. We are given one proportion over here of male students who did yes on a test, and we're asked if it's higher, so that's going to be a one tail, but we're not giving anything about what the females did, so we're going to have to guess that. So I'm going to guess that it was higher, and by like 10%, so 0.85. So we'll need to plug those two proportions in to get our effect size, and plug that in, and of course we get samples out. There we go. All right, so here's the ChiSquared test. Imagine with the two sample test, the logical extension was the ANOVA. For a ChiSquared test, it's the logical extension of the two proportion tests. We can ask if a table of observed values are any different from a table of expected ones. This is also known as a goodness of fit test. So a classic example comes out of a genetics context. So do a certain proportion of phenotypes from we get from experiment, do they differ from the expected theoretical proportion, say 9 to 3 to 3 to 1? So we see here now there's not just two groups, there's really as many groups as we would want. So the null is there is no difference, so the thing we observe is the same as the thing we expected. And then the alternative is there is at least some difference. So we're going to guess a medium effect here. And now we have something different. We have a W test. So they're going to be a little bit different. So a medium effect size is 0.3. And now for this chi-square test, we're going to need something called degrees of freedom. So that's the number of proportions minus 1. So we have 4 different proportions we're looking at. 3, 4. So that's going to be 4. Also our phenotypes. Minus 1. So that's 3 degrees of freedom. We're going to need that when we use this power chi-squared test. We have effect size, but then this df, that's our degrees of freedom that we need to plug in there. And then again, significance of power. Now, W test effect size calculation is a little different here. It's going to be the square root of this chi-squared value, and then divided by the number of samples, and then the degrees of freedom. So we'll again need degrees of freedom. Chi-squared, that value is just the sum of all the observed values minus the expected values, squared divided by the expected. So we'll see what that looks like in some of our practice examples. For R here, power chi-squared test, effect size 0.3, 3 degrees of freedom, and then standard significance level of power. We get 121 or 122 samples that we need for this. Here's some practice. You can pause now and try this out yourself. Okay, for question 1, we get this data here about 200 employers. So this looks like numeric data, but this is actually just summed categorical data where 200 people were asked or determined their ethnicity and gender was determined, and then it was summed into these different tables. So there's 60 which are white and male, 65 which are white and female, etc. So what we're interested in is if it differs by gender. So if they were equal, the expected ratio should be the same as the overall ethnic ratio. So overall white is 65 by 65, so that's 62.5, and so forth. So we'll just look at males here and see if these observed genders ratios among ethnic ratios are different from our expected overall. So this is where our chi-square comes in. It's going to be observed minus expected. So we need to sum up all these four different ratios. So the first one here is going to be our observed 60 minus our expected, divided by the expected, and so forth. So it's black, this is American Indian, and this is Asian. And this gives us 4 values, which we sum, because it's the summation symbol, to give us 8. So we can plug that into our effect size. So chi-square will go here. N, which is 200. Degrees of freedom is 3, because we had 4 groups, which gives us 0.115. Plug that in and get us 825 samples. So 2 here, we are interested in these proportions if they're different from essentially parity, 1 to 1 to 1 to 1 of students by year. So we've seen this kind of data before. It's proportion, so we can get our proportions out by counting. And here we get the chi-squared. We can see that there's 1, 2, 7 freshmen. So we expect only 5. There's a total of 20. So that's our observed minus our expected, squared divided by expected, and so on for all of them. We see here that, like, say, sophomores and juniors, they were exactly what we expected, but then freshmen and juniors were different. Gives us a total of 1.6. Plug that in, get effect size, and we plug that all in to get our total of 411 samples. Moving right along here, we've arrived at simple linear regression. So this, instead of those proportions or mean t-tests where we have, at least in some way, like some sort of categories like gender or number of cities, that sort of thing, this is just 2 numerical variables that we're looking if there's a significant relationship. So 2 numeric variables. So and you typically, the results of this will be a scatter plot. So 1 variable on the x plot and 1 on the y. So example would be like, is there a relationship between height and weight in college males? So we don't have background information, so we're going to say it's going to be large. Again, for all these, we're just guessing for the first part. Now for these, the effect size, these are F2 tests. A large effect size is going to be 0.35. And when we get to the R code, we're going to need to know degrees of freedom, because it turns out both simple and then we'll see next multiple linear regression use the same thing. Simple regression is just a limit case of 1 predictor variable. So our degrees of freedom are going to just be 1 here. Important thing to note, our output is actually not going to be in sample size like the other ones. It'll actually be in denominator degrees of freedom. So we're going to need to round up and add 2 to get our sample size. You'll see what that looks like. Then to get effect size, if we need to calculate ourselves, it's going to be the R value, which is, you might have seen before, it's called the correlation coefficient. You can get that from the R squared, which is the goodness of fit. And in a test, you should use the adjusted R squared. So for our power F2 test, we're going to need to plug in U, and then we're going to actually get out V, so we're not going to actually add anything to V. That's going to be denominator degrees of freedom. We'll need our effect size and then significance level and power. So let's take a look about this with our example. So we had 1 predictor variable, because we're just looking at simple linear regression, which means there's just 1 predictor variable. And then our effect size, significance level and power. And then we see we get here this denominator of 22.5. So I just used an R, I just rounded that up to the nearest, so that's going to be 3, and then add 2 to get 25 sample size. So that's how you do it in R here. So try this yourself. Make sure you can get a handle on this. Alrighty, this first one here, we get the raw data ourselves. We could do everything ourselves. So what I do in R here is I actually create variables of yield and height. Just enter those in. And then I can run a simple linear model. So I just called it linear model. Then I use LM for linear model, and I'm seeing if height can be predicted by yield. And then I get a summary, so I can get out this adjusted R squared. And to get R, I know I just need to take the square root of the R squared, and that gives me 0.53. Plug that in. Once again, this is 1. Gives me 14.96, so I round up, add 2, and then get 17 samples. For 2, I'm not given any information, so I'm going to guess an effect size, and then, of course, 1 predictor, so 1 degrees of freedom. Put that in there to get 25 samples after rounding up. Okay, multiple linear regression isn't going to be much harder. It's an extensive, simple linear. Now there can be more predictor variables, so you can say, instead of just can height predict weight in males, we can say can height, age, and time spent at the gym predict weights. Another thing here is you can actually use interaction effects. We're not going to do that, but that's an important thing you can do. And then finally, while I talked about simple linear regression, a lot of times the results you see are like scatter plots. You really can't do this in more than 3 dimensions, so you usually don't see results like plots. So for this example here, we're going to guess a medium effect. So that's going to be a 0.15. And now the numerator and degrees of freedom are going to be different. So that's going to be the number of predictor variables. So we have 1, 2, and 3. So that's going to be 3. And then output, once again, is going to be a denominator degrees of freedom rather than sample size. So we need to round up and add the total number of variables. So our total number is 1, 2, 3, and then, of course, weight. So for a total of 4. We're using the exact same function, power F2 test. We're just changing the numerator degrees of freedom to match the fact that we're using multiple linear regression. You get effect size the same way. So for our example, plug these values in to get a total of 72.7 from our degrees of freedom, and then I'm going to add, our total number of variables after rounding up to get a sample size of 77. There we go. Try this yourself. Make sure multiple linear regression makes sense. Okay, for 1, we are given the raw data again. So I just made some quick variables and then made another linear model. So I'm predicting height with yield, weight, and fertilizer. Got my summary out so I can get my adjusted R squared. Plug that in to get my effect size. Put that in there. We had 4 different variables, 3 different predictors. So the 3 predictors go here. We add the results of the total variables 4 to get 18 samples. For 2, we're given no information, so we get to make a lovely guess. But we do need to realize that there are 1, 2, 3, 4 variables that we're trying to predict population with. So the degrees of freedom is 3, and we need to actually add, there's a mistake here, not 4, but 5. So we need a total of 37 samples. There we go. Okay, let's wrap this up with correlation. So it's very similar to regression, but it's not identical. Usually use correlation when you're not sure if one variable like sort of causes the other or affects, causes the other. So like correlation is not causation, that sort of thing. if you're just looking at relationship, not directionality. So you might ask, is there a correlation between hours studied and your test score? So we can just try a large correlation, and for correlation, so R, that's the correlation coefficient, a large one would be 0.5. So this is called a power R test, so R for the correlation. So you just need to enter the correlation coefficient, significance level, and power. So this is one of the simplest things you have to do for tests. So we can plug in our large effect size, standard significance level, and power to give us 29 samples. Pretty simple. Try that out, make sure it makes sense. Okay, great. For our first question, we get the raw data of height and weight of males. So what I do is I just made variables in R, then ran a correlation test with just the function core of height and weight. It gives me an R value of 0.37. Plug that in, 55 samples. For 2, we're given no information, so I guessed. Plug that in, got me 29 samples. So there you have it. There's the end of those green tests, which could be used with the power packages. So now I'll end here and pick up in the next segment with some more non-parametric tests. Thank you.